everyone, how are we doing? It is Tuesday morning, day of the test. Oh my gosh. I did the water turned off, so I had to wait a little bit this morning. They're still wet. Wake up and they say, the water's turned off at your apartment complex. You say, oh my gosh, why would you do that? Why would you do that to us? They say there's a leak, and I say, okay. What questions are there right now? What test questions? We'll put the review in the chat. Good to see you, Jesse, Carlton, and Ella. Review 2 in the chat. Newbot is posting about reviews right there. What questions are there as we start to review right here? Oh, I think I saw Jesse said something. Let me see. Oh, sorry. Ate some granola this morning. Can we do probability? Of course. Let's do probability review. Let's go right here. There's like flax seeds and everything in it. So stat to a 1. Probability review. Let's do it. Okay, so when it comes to probability, there's key terms you need to know. What are maybe, I'd say, like, can you think of 4 key terms? Can we get 4 key terms? Well, coin flips are one. I'll drink some coffee. There we go. Good coffee. What are key terms? Any key terms? The addition, there's the addition rule. So addition rule. Anything else? What else do you have? Multiplication rule. Anything else? And then we'll go over these and talk about what they are. Hey, Mason, what's up? We're talking about the key terms. Complement. Great job, Ella, right there. We'll throw points out. Complement rule. Any other key like words or phrases to know? These are really great. These are good stuff right here. We can do 10% coming up here in a little bit. You bet. Complement. And I would say there's some big things we should know. These are big. These are big too. I think so. Let's put key terms right here. Words like disjoint, mutually exclusive, and independent. Dependent. Can anyone think of anything else? Independent. Great job, Carlton. That's where I was thinking. And then that use not. Oh yeah, that's the complement. So these are a bunch of key terms we need to know and be able to define all these things. Or we could say sample space too. Sample space. I think that's about everything. Maybe we'll put like probability right here also. Okay. So let's think about how to describe all these things. Probability is what? Probability is what? What is probability? Probability is what? It would be, I would say, a value between 0 through 1, telling us how likely or unlikely something is to occur, which actually one of the first rules of probability right here. So that's just my definition. These are not textbook definitions. You can go like, what is the definition of probability?
Probability means the extent to which something is probable, the likelihood of something happening or being the case.
Likely of something happening. I don't like when someone uses the same word, like how probable something is, but how likely something is to occur. Which is a value assigned between 0 and 1, 1 meaning it must occur, 0 meaning it can't occur. So we've kind of got the first rule of probability right here. So that's the first thing. And then the sample space is what? I think a lot of people forget what sample space is. How would we define what a sample space is? What is a sample space? What is a sample space? Good to see you here, Michael. We're practicing some review right now, thinking about these key terms we need to know for probability. What is the sample space? And these are very important. Like right here, knowing probability ranges between 0 and 1. If you do things like with the addition rule, to where if I told you what is the probability someone has a cell phone is 70%, and the probability someone has an iPhone is 0.50. What is the probability someone has a cell phone and or an iPhone. So right here, I want you to think about this and the errors people can easily make. So this is why knowing the terms is going to help right here. And I want you to think about what's wrong with this, and this will lead to other questions when reviewing probability right here. And I want you to talk about this. This is a tricky question. So what's the deal with this question right here? Can't have that since they add up to, well, kind of. So if you notice right here, think about what we have. This will lead to another concept, which we'll mark here in a second, this is the people who have cell phones, right? So these are cell phone people. And then what about iPhone people? These are iPhone people. Well, actually, you know what? The way it would look is it would be like this. Here's iPhone people. So iPhones are cell phones, exactly. So these are completely jointed, you would say. Sometimes I call it that, but they're not disjoint. So if someone has an iPhone, that's IP for iPhone right there, then people who have iPhones have cell phones. So it's not everyone who has a cell phone has an iPhone, though, because the probability of cell phone is 70%, and the probability of iPhone is 50% right there. So there's, a lot of people with iPhones, but then there's people with cell phones who don't have iPhones. So with this in mind right here, what happens if you just add these right here, which we can see with the addition rule? So it wouldn't be 1. The answer to this question is, and we'll do independent coming up here next, you got it. The answer to this is a trick question, and right now we don't have enough information to solve it. So the answer, but what's wrong with 1.2? Why can the answer not be 1.2? Oh, and then I think people are saying, right, so it can't be 1.2 because when you do that right there, you're getting a probability outside of 1. So if you were to do this, you'd be like, something's wrong right here. And we could say, trick question. These are not disjoint and can't be added together. So this is a trick question right here because if you just added them together, you would do that. So now we can talk about the addition rule a little bit. 2 events that are disjoint, which is the same thing as mutually exclusive, can be added together to find the probability of A or B occurring. So this is the actual case of it. We got the trick question below. And let's say people can only have one primary phone. Like you have to list your primary phone. Does that make sense? We'll do independent coming up here, Martin, coming up. Does independent happen or occur at this? So that's a good question, Martin. We'll be listing that here in just a second. There are sometimes trick questions on the test. So people can only have one primary cell phone. When we look at data across the US, we see that 60 or 50%, 50% of people have iPhones. It's iPhone like this. And 30% have what is it? What's the other one? Oh wait, it's Google. Why can't I think of it? Google phones. Google phones. And 20% have Samsung, right? Samsung's the big one. Galaxy phones. Android, yeah, Android. Oh, let's go Android. And 20% have other phones. Okay. You can only have one primary phone. Does that make sense? You can't say, hey, this is my primary phone and this is my primary phone. You'd have a secondary phone. So we would say here something like, what is the probability someone has an iPhone or an Android? So pretty easy question using the addition rule. What is the probability someone has an iPhone or an Android phone as their primary phone? And it's 80%. Because think about this. If your primary phone is an iPhone, what does that mean about it being an Android? This is what disjoint means. And we'll define disjoint here in a second. But what does it mean if your iPhone is your primary phone? What does that mean about Android? If an iPhone is your primary phone, what does that mean? It can't be Android. So as soon as you say yes to one, if something is disjoint, the other answers are no, because they exclude each other. That's what mutually exclusive means. So you have to know the terms here, and this is why we're doing the terms, to say, like, if something is disjoint, if the answer to one is yes, The answers to the others have to be no. So, are your grades disjoint? Like when you get a grade in Stat 201, are the A, the B, the C, the D, the F at the end of the semester, are those disjoint? The grade in Stat 201 you get. They are disjoint. Because if you get a B in Stat 201 or an A, if you get a B, you can't get another grade. Like that's your grade this semester. And you say, what if I retake the course? Well, I'd be taking it twice, which then you could have. You could have an A and B if you take it twice, because then double the grade, double the power, exactly, double the fun. So does everyone understand? I think the addition rule is a little bit easier, but a lot of people get confused on the idea of like disjoint / mutually exclusive. That's a very common forgetting what those terms mean right there. Very, very common. So that really disjoint means, which is the same thing as mutually exclusive. If A occurs, what? If event A occurs, like we have an iPhone as our primary phone, what does that mean about B? And this is the way to test it, to be like, somebody has an iPhone as their primary phone. What does that mean about other things? B can't occur. So they're disjoint. There's no overlap between them. This example we did way down here with the other thing was a trick question because someone could have a cell phone and could have an iPhone. Like those can occur at the same time. Like you can be like, I have a cell phone and I have an iPhone. That's not disjoint. But if you say your primary phone can only be one phone, it can either be an iPhone or an Android or some other type of phone. Well, you can't have an iPhone and an Android as your primary phone when we only allow one primary phone. We're not going to allow you to have multiple primary phones. So if A occurs, B cannot occur. And the number one way to check this, which please try to check these things, say to yourself, I know someone's iPhone, I know someone's primary phone is an iPhone. And then you would say what? You would say, I know someone's primary phone is an iPhone. Is it what? I know someone's primary phone is an iPhone. This is the way to check disjoint. You'd say, I know someone's primary phone is an iPhone. Like, let's just take that as the case. Like, someone has an iPhone as their primary phone. Then to check to see if it's disjoint, you would what? You would say what? Well, kind of, and that's what we're asking. We're asking, is it mutually exclusive? To check to see if it's disjoint, you would say, well, and so in this context, what is B? So you'd say, I know, can they also have an Android as their primary phone? Exactly, Jesse. And the answer is no. It is impossible. If the iPhone is your primary phone, it is impossible that an Android is your primary phone. And that proves to you that they are disjoint. And since they are disjoint, you can what these probabilities now? Since they are disjoint, you can what those probabilities? Since they are disjoint, you can what those probabilities? You can add them. Exactly. So make sure to check it that way. And often, sometimes where confusion is when we get to the multiplication rule. So the multiplication rule is, I think, where people start to get to confusion because we're going to use another term here, which we have listed down below. So the multiplication rule states two events that are, or we can say probabilities, two probabilities that are independent of each other can be multiplied together to find the probability that A and B happen at the same time. Okay, so we are going to start with a trick question right here. On any random day in Knoxville, there is a 1% probability of snow and a 1% probability we get school off. What is the probability that it snows and we get the day off? Okay, so we don't need to know margin of error. Margin of error is not on the test. Good question right there. Thank you, Martin, for asking. So think about this question. We are starting with a trick question right here. I'm giving hints by saying this is a trick question. So, and then I want you to think about why it's a trick question and what the multiplication rule says to us. So we'll give it a moment right here. These are really good sort of like, well, what does this rule mean? How does it work? Two probabilities that are independent of each other can be multiplied together. Find the probability that A and B happen at the same time, which is sort of asking. Exactly. So Jesse, wouldn't you say school is what on snow? Like the probability of school would what? You know, you're on the right track. People are seeing it. Great job, everyone. So you would say the probability of us having school is what? School is dependent on if we have snow, right? So getting school off, the probability would probably what if it snowed? If it snowed in Knoxville, the probability of getting the day off would probably what? Think about everyone when it's snowing outside and they're like, because they're not thinking it's still a 1% chance, right? Then they're thinking the probability is increasing of school being off tomorrow. And they're right. They understand here that the probability of school off is going to depend on if it snowed. So the issue is we can't really multiply this right here with this information, because what this would tell you is if you did it incorrectly, you would do the following, and you would see, should be that, right? No, I think I went too many zeros. I should know how to do. Decimals are weird. No, had it right the first time. Which is basically a 1 in 10, 100, 1,000, 10,000 chance. Like 1 out of 10,000 days it'll snow and we'll get school off, which just doesn't seem right because we've seen it multiple times. We know that snow is not that likely in Knoxville, but when it does snow, we're more likely to get school off. So the probability of school off depends on if there is snow. Okay, so that's not how we do the multiplication rule. So what is this term that we're thinking about called independent dependent? So when you go down here to independent, the probability of A, what if B occurs? The probability of A will what if B occurs? So independent would mean what? And Mason's basically got it. That is correct right there, Sydney. We would not multiply those. That was a trick question. You would say, if that was listed, you would say this is a trick question. Since we don't have a lot of written responses, we don't do many trick questions like that anymore. Because you'd have to write it out and say, like, this is a trick question. We'd usually throw like one of those on a test worth like 2 points. Be like, we cannot multiply these because of the multiplication rule. Yes, the probability of A does not change. Or we could say change, or depend is part of it. So I might, depend is true. Like, that is what you said there's Jesse. So a lot of times I avoid does not change. A, Ella said exactly what I said. The probability of A does not change if B occurs. So in our previous example, we were saying if it snows, that is going to change the probability of school. So you can say the different way of saying it here for dependent. So we're literally going to take the same sort of definition right here, drop it in, bold it up. There we go. And go, the probability of A changes if B occurs. And I want you to think about something right here. Which of these two, or is something that is disjoint, is it independent or dependent? Now be careful, they do not mean the same thing. So would you, that for two events can't happen at the same time? Well, if two events can't happen at the same time, they are what? Kind of, there's two ways of saying it. If two events can't happen at the same time, they are disjoint, which is the same thing as mutually exclusive. And disjoint events are what? Now be careful, these are not synonymous. They are super duper dependent. So that is true, but are all dependent events disjoint? Are all dependent events disjoint? That's not the way it goes. So the way it goes is disjoint events are dependent. Dependent events aren't always disjoint. And this is where knowing the terms helps, because we're saying if A occurs, that what right here? If A occurs, then B cannot occur. So think about that. It just what the probability of B. If things are disjoint, if A occurs, B cannot occur. So by A occurring, it did what? To say they're dependent now. By A occurring, it just did what? So since A occurred, B cannot occur. A occurring does what? And you could do B occurring, whatever, whichever order. If A occurs, B cannot occur. So the probability of B just whatted because A occurred. The probability of B just whatted. So if A occurs, B cannot occur. So the probability of B just whatted because A occurred. Does that make sense? I think this is a higher level understanding right here. It just changed. And you don't want to memorize, be very careful. You want to understand, like, disjoint means that there's no overlap between the events occurring. So literally knowing one occurs would tell you that the other did not occur. So that does mean they are dependent. Like, think about this. Making an A in stat 201 depends on if you make a B. If you make a B, you didn't make an A. So independent is a different term, though. Independent means knowing that something occurred does not tell you anything about the other events occurring. So this is where the practice comes into play. I think we only need one more thing down here. The set of all possible outcomes. So what is the sample space of flipping a coin? One of the easiest questions to ask there. We'll go back to multiplication rule here in a second. What is the sample space of flipping a coin? What is the sample space? It's the set of all possible outcomes. Heads or tails. Yep. Then you could like list it. A lot of times I like to draw these out. If you've watched me work a lot of the problems, I'll usually put right here the event, the probability of said event, and we'll put like here heads and tails, and we'll put the probabilities associated. And the sum of the sample space is equal to what? Usually we write them as disjoint events right there. The sum of the sample space is equal to what? Which is actually rule 2. And great job right there, it's equal to 1. So if you list all the things that could occur and then you sum them up, you will see the probabilities all add up to 1. So very, very key right there. And great job. Thank you everyone for being here and reviewing. Good review time of probability, which was one of the earliest chapters we did. So 2 events that are independent can be easily multiplied together. So your favorite baseball team has a 30 or no better has a 70% chance of winning this season from historic data. Your favorite basketball team has a 60% chance of winning this season. What is the probability both your teams lose? We'll go win first. That's the easier one to do. Okay, so think about this. What's the first thing? So i.e. baseball and basketball. Baseball wins and basketball wins. Okay, so the reason I'm writing it this way is because in the multiplication rule, we use and to multiply things together. So we have the probability baseball wins and basketball wins. Pretty easy to do right here. What do we got? No, it wouldn't be 0. So I'd say it's impossible that both your team wins. Don't worry, Martin, 100 points there. So 0 would say it's impossible that both your teams win. So we can just multiply both these probabilities right here by subbing them in. And good work, Martin, for first answer right there. Let's throw another 100 points. Remember, answer these questions, practice along with us right here. Nothing wrong with getting them wrong. It means you're practicing and you're here. So we're just literally changing this over to the probability and the multiply and then going right here. So that's going to be the probability right there of baseball and basketball winning. So then we could simply change this to lose. Baseball loses, sure. And basketball loses. So this, once again, is using the complement rule here. So we'll come back to this in a second, but complement rule is really easy to write. The probability of not A is 1 minus probability of A. So the probability of not A is 1 minus probability of A, and there's a lot of cool things you can do with this, i.e. like 1 is equal to the probability of A plus the probability of not A. And you're actually seeing right here the addition rule in place, because think about this. Why does the addition rule work right here? Because think about this. We have your team winning and not winning. We'll just say losing. There's no ties in these games, I think. So winning and not winning. So why can you use the addition rule right here? Because winning and not winning are what? Think about when your team wins or not wins. They are disjoint. Does that make sense? So you can actually use the addition rule, and then winning and not winning is everything that would occur because your team either wins or not wins. So then we've just reviewed what the sample space is. The sample space is all possible outcomes. We could put here adds to 1. So you can literally make a sample space right here from this by saying either my team will win or not win tonight. There you go. So there's a lot of overlap between these rules right here and how they're used. The terminology is very important, so knowing it is going to be huge. And I think people are already showing how to do the last one right here. We need to find the probability of lose. I'm going to do a more complex rule in at least one, or more complex question in at least one question. So the probability of lose right here. So probability of lose for, we'll say game 1. Probability of lose game 1 is equal to 30%. So that's that. Probability of lose game 2. We're just putting a game 2 right there is equal to 40%. And there we go. And that's, there people are getting the point 12. But now we get to one of those at least one problems. So now we're going to do an at least one problem. So let me put this on a new page. And let's turn it into an at least one problem. Okay, so here we go. A lot of people hate the at least one problems. They're a little bit fun. So let's say an at least one problem. So these are the at least one problems. What is the probability that your baseball team loses at least one game in the next 5 games? Okay, so you got a lot of extra information right here. And the at least one problems, I always say write a sentence to start. So don't just try to, well, first off, start marking your probabilities. There's extra information right here, but you need to write a sentence. 1, write your sentence. So that might be right, Jesse. That might be right. Let's find out. So loses at least one game in the next 5. Okay. 2, 3, 4, 5. Let me double check my work. 2, 3, 4, 5. Yes, Sydney and Martin have it. Yep. Okay, let's show how they did it. So 100 points right there and good practice. Sydney and Marcus are correct right there. I was like, it should be somewhere around like 80s, 90s. I was thinking in there, like just thinking theoretically what it should be. So when we write our sentence right here, we're thinking about 2 things that could occur that encompass everything. 2 things that could occur that encompass, that list, that are a sample space. Well, that show everything. That's what a sample space is. Okay, so you did basketball. Oh, there you go. That's, yeah. So yeah, I bet, yeah. Let's see, wait. 2, 3, 4, 5. Yep, there we go. Yep, that was right. Good job. That's why I have 2 probabilities listed. The way I get these better than I know, right? So with this right here, we already have one of the sentences or one of the parts of the sentences loses at least one game. Loses at least one game. They will either lose at least one game or what? They will either lose one game in next 5 or what? They will either lose at least one game in the next 5 or what? So think about your team is playing and you've got 5 games. You would either lose at least one game. They lost 2 there. They lost 1 there, maybe 3 there. They will either lose one game, at least one game, or they will win all of them. That's either they're going to lose at least one or win all games. And this is equal to what? Because we just listed everything that could occur. So they will either lose at least one game or win all the games. So since we've listed everything that could occur, it equals 1. Now we know that this becomes addition right here. And when we say they're going to win all the games, now we do have to assume independence right here, because winning all the games means, and we're going to use the probability up top, this one, because that's the baseball team, right? Baseball team, yep. And so if you want, we can just remove out this if people are getting confused. That's extra information not needed in the problem. But no, don't worry. Sometimes we do that. You never know. Lose at least one game in the next 5, or they're going to win all their games. So now we have to figure out the probability of winning all the games. But if you want, you can start algebraing this over while you're doing it. And you can see if we do the minus, because we're just going to minus it from both sides, and then you get this right here. So now we know the answer to this, and all we have to do is solve this and then figure out the answer. So what is the probability of winning all the games? Winning all the games means the first game they whatted. When they played the first game here, they whatted. If they're going to win all the games, the first game they would what? Won, and the second game they won, and the third game they won, and the fourth game and the fifth game they won. So this is where we get 0.7 times 0.7 times 0.7 times 0.7 times 0.7. And the easy way to abbreviate this is what? The easy way to abbreviate that is what? And Jesse, great job right there showing the work. The easy way to abbreviate that is what? Boom, right there. So we've just abbreviated it, and then we go here and go 0.7 2, 3, 4, 5. And there's, whoops. Should have a guesstimate of what the answer is. There's the answer right there people had. Once again, be careful typing it into the calculator. A lot of errors can be made. And then watch as you do it. Maybe double check it. It's easy to make errors, but you should see the numbers getting smaller. Multiplying decimals get smaller. 2, 3, 4, 5. And that is to the 5th power. You can probably do, well, if you go to the scientific on this, you can do it that way. And then 1 minus. There we go. Good stuff right there. And that's the answer to the question. So that is the math right there. There's the answer listed right there. And that's the probability they lose at least one. So basically, this problem had to do with both dependent. So there was no dependent in this problem, I don't think. Well, yeah. I mean, if you consider the disjoint rule here, dependent, kind of. This was the complement. This was a complement problem. Yep. So what would this mean right here? And Savannah, good question. What does, and let's look at this. What does 1 minus 0.30 to the 5th power mean? First off, what is 0.30 to the 5th power? So what is 0.30 to the 5th power right there? So 0.30 is probability what? We can start with this. 0.30 is probability what? What is 0.30 right there? This is a totally different question right now. So what does 0.30 mean? What does 0.30 mean? Probability of losing. What is 0.30 to the 5th power? What does 0.30 to the 5th power mean? What does 0.30 to the 5th power mean? Losing all 5 games. What is a word we use when we use the complement? I don't know if I listed that right here. Well, there it is. The word we use with the complement is not. So you can think when you do 1 minus this, you can just go 1 minus 0.3, and now just use the word I told you to use. And what are you going to get if you substitute in that word here? It's the probability of what? So now we just did 1 minus it, so use the trick I just mentioned with the complement, and it's what now? Use the complement trick I just mentioned. So what word, and I think Jesse said right there, we're going to say not losing all 5 games. So that is the probability of not losing all 5 games. So now reword this, because not losing all 5 games means you did what? Your team what? If your team did not lose all 5 games, then your team did what? Be very careful. This is where a mistake can usually happen. Well, be very, won at least one. So that's the probability of winning at least one, because they did not lose all 5 games. So that's the probability of not losing all 5 games, which is the same as saying we won at least one game. And just breaking it down to its parts, being like, okay, 0.3 is the probability of losing. 0.3 to the 5th power is probably losing all 5 games. 1 minus 0.3 to the 5th power is not losing all 5 games. If we did not lose all 5 games, that means we won at least one game. And so the more you work these problems, the better you get at them. Savannah, thank you for asking that right there. It just comes down to practice with these problems. And then what you can do a lot of times, here we'll do one more of these, then we'll switch topics, is you can list the sample space. So creating a sample space. And so I want you to see what you can do. Like if I were to say, your favorite baseball team has a, let's say, 80% probability of winning. They are awesome. What is the probability they win one of their next 2 games? And I know the answer. 500 points online if anyone can figure it out in the next 15 seconds. 500 points if anyone can figure out in the next... Let's see if anyone can get it. Jesse, check your decimals. Check your decimals, Jesse. Check your decimals. Let me think. Jesse's basically got it, I think. Jesse's basically got it. I have one sheet of scratch paper. One sheet of scratch paper. That way, because if you have like 20 sheets, it's gonna be hard for us to tell if there's anything on it. It's possible. Ethan, you're correct. It is possible. So let's look at this as a sample space. What is everything? Great job, Joseph, right there. What is everything that could occur? So we have the event and probability of the event. What is everything that could occur? I'll give you a hint. Your team could lose and lose. And then Shinna right there has it perfectly. Yep. And win and lose and win. So the probability of lose is equal to 20%. What rule did I just use right here to get this? I just quickly did a rule that got me the probability of lose because we're only going to allow win and lose in this. Those are the only two things that could occur right there. How did I quickly do this? And this is like the car problems. If you remember the car problems where it's like, what's the probability of one of your cars in your repairs? Complement with an E technically, and I didn't know that for multiple semesters. Complement right there. That's the complement rule. So what is the probability of lose and lose? Lose and lose, which is not very likely. Now, you know what the beauty of this problem is? Watch this. Complement rule right here. Multiplication rule right here. And to find the answer, we need to use the what? To find the answer to this problem, we need to use the what? To find the answer, we need to use the what? That's the beauty of this problem. We need to use the addition rule. Because either your team will lose the first and win the second, or your team will win the first and lose the second. So we can write it as a sentence, trying to get beyond it. So if you want to, whoops, oh my gosh, what have I done to this? If you wanted to write it as a sentence, if we appear back on it, the sentence would look, it's not going to let us write on it. Okay, it'd be the probability of win, or right the way I did it, probability of lose, lose and win, or probability of win and probability of win and lose. And there it is right there, shown as the mathematics up top. So the reason it is 0.32 is because the two possible outcomes of you winning at least one of the next. Yeah, you just add them. It's actually Shinner right there. You just add them. Because could your team lose the first and win the second, and at the same time win the first and lose the second? Is it possible that these two things could occur at the same time? Like this could occur and this could occur at the same time. Is that possible in the next two games? And so you've just said that these two things are what of each other. You've just said that these two things are what of each other. Be careful. Use the perfect word for this. I said they cannot occur at the same time. You've just stated they are what of each other. Disjoint. Exactly. And that's why you're adding them right there. So be careful. I know we could say another word, but don't say it. It is true that it is that, but don't say the other word there. And then we are assuming right here that your team losing the first would what on winning the second, or your team winning the first and losing the second. We are assuming what here? We are assuming what here? And you can see it up here with the mathematics also, where we did the math to find out these probabilities. We are assuming what right there? We are assuming what? It does not influence, exactly. Well, and we are multiplying and does not influence, and Jesse, I think, has it right there, means that they are independent, that the probability of your team winning the second would not be influenced, i.e. is independent of winning or losing the first. So that's what we are able to multiply right there. And the question might even say, assume, I mean, if it has a numeric input, you have to enter in an answer, but listing out the full sample space. And then you know what we can do? What's a final check we could do on the sample space right here to see if we have the sample space correct? What is and we're literally almost covering pretty much every rule. All the probabilities are between 0 and 1, And then rule number 2, we have literally done every rule to probability by doing this problem right here. We can do what? They add to 1, exactly. So if you've listed everything that could occur as disjoint things, whoops, I think I typed something wrong. There we go. And there you go. So they add up to 1. Yep, 32 plus 4 is 36, plus 64 is 100. So now you've shown that this adds up to 1 right here. So the probability of the sample space equals 1. And literally, that is... Who feels better? Does anyone feel better about this chapter? That's a 45 or 43-minute review of pretty much everything in the chapter. That's about... I think that's pretty much all I can think of. Yeah, so Jesse, good question right there. You have to know the terms. You have to know ways to make up your own problems. So we did all the different things right here in at least one problem, an addition rule, multiplication rule. Good stuff right there. What should we do next? It's your call, and thank you everyone for being here. It's your call. Do remember this. Did this seem way easier this time? For those watching this in the future or watching this right now, maybe you were stuck and you haven't said anything, that's all right. But who feels like this seemed way easier now? And then if you say yes, I want you to say how many times you think you've heard this. So if this seemed like way easier, I want you to say yes, but then I want you to think of how many times you've heard me go over this. Like this is like the how many times you've heard me do a disjoint problem or independent. So James, great to see you here, James. How many times do you think you've heard me say all this stuff? Like I'm interested to hear, like it's only through repetition we learn stuff. Because if it is your first time hearing this, you're probably like, what in the world, that whole complement rule? And I try to go slower the first time because we do a whole lecture on this that lasts about, was it 75 minutes? So yeah, you watched the speedrun too, Shinna? Great. And think about this. We just did the whole chapter basically in 40-ish minutes. That's like half the time of lecture. So if you're like, wait, this was easier, I was almost going twice the speed of lecture. So I went twice the speed and you were like, it was easier. But it's just because you know it better. It's like if I try to teach a child how to count, you got to be like, okay, 1, 2, but you've done that so many times, you're like lightning speed, you know, now. So remember, with test 3 material, it's really going to boil down to, you know what, let's talk about regression right here. So I've got data from a semester, long time ago, I pulled this up. So it's anonymous data. There's no names attached to it. Just want to put that out there. This is anonymous data. This is real data. So once again, anonymous, no names attached. It's aggregate data, shows you what's going on right here. And I want to show you what we have implied right here. So check this out. You ready? Let me put it in the 4513 stat 201 regression review. We'll wait on that. Let's just do a review of regression. Here we go. Let's go and take a look at regression. So we've done this a lot, and hopefully we're helping out as many classes as possible right now. How many things are you going to have to write interpretations for on the test? How many things are you going to have to write interpretations for on the test? How many things are you going to have to write interpretations for on the test? 3 things. Let me tell you the bad interpretations to start. If you're watching this now, the only way you're going to get this down, Jesse knows right there instantaneously, and so does Sydney. You know the 3 things. And so I'm sorry, like Jesse, and great job, Jesse. And great job, Janeki and Ty, and so many people here. Might be just talking to the people who know what's up. And if you're watching this, join in anytime. Join the questions, ask questions, whatever you want. We're here to help out. Because a lot of people know where I'm probably going with this. Let's look at how many Facebook friends people have. And Facebook friends could be related to how many hours you're on social media. So this is right here. So hours on social media. What would you expect, a positive or negative slope to this? And this is old, only Facebook. God, Facebook was so big back in the day. What would you expect here, a positive or negative slope? Just think about this. People who are on social media more, we would probably expect what for their Facebook friends? It's kind of crazy. People, some say they're on social media. I think we allowed for like, there's 24 hours in a day times 7. See, that's impossible. Weekly hours on social media. So we can actually remove these right here, the people who put 200, because even 150, you're not sleeping. So what I'm going to do right here is I'm going to go to redo, automatic recalc. I'm going to go to these points, hide and exclude. Why did I exclude those? Not because I didn't like them. First off, 200 hours on social media a week is what? First off, 200 hours on social media a week is what? 200 hours on social media a week is what? And I could probably make a fair cutoff right here. That's literally impossible. So the answer they gave is just, you can't, that's not possible. So I just said, is beyond insane. It's just not possible because there's only 168 hours in a week. So then I removed things above 100 because like at 150, you're only sleeping 18 hours over 7 days. You're getting 2.5 hours of sleep, and then you're constantly on social media. So I don't think people are averaging 2.5 hours of sleep, 2.57, 1.4, oh, it's a seventh. Yeah, of course it is. And so I don't think people are doing 150 hours. So I said, okay, my cutoff for like what I think is possible is 100. And if someone says they're on social media 100 hours a week, I mean, some people are on social media about 100 hours a week. Like morning, noon, night. You look someone on their phone, you're like, I'm on social media. I just got my phone on all the time. Twitter, everything's whatever. I don't know what people use these days. So now we're going to add in the regression line right here. Oh my gosh. This line looks about what? That line, whoa, I didn't even expect this example. That line looks about what? That line looks about what right there? Wow, this is a cool example. I definitely know it relates to test questions. It looks flat. Estimate the slope of the line. Don't look at the equation. Just don't even worry about the equation right here. Just kind of take a guesstimate of the slope. I know you can look at it over there, but it's closer to what? Since it's flat, it's closer to what? This is an important concept. This is an important concept. It's closer-ish to what? Closer to zero. Closer to zero. Now, you see it right there. There's the slope right here. So it's hours on social media. I'm just making this easier to read right here. We're going to just abbreviate down a little bit. Sure, we'll round up as we should. And we'll say social friends. Or Facebook friends. Facebook friends. There we go. And we'll round this right there. And there's the equation. So we'll talk about the equation here in a moment. But I want you to think about the p-value for a moment. The p-value for this is going to probably be high or low. And I'll explain why it is that in a moment, but let's see if you know. So take a, in the poll here, the p-value is probably high or low. The p-value for this is probably high or low. What do you think? I could take a guess of the p-value here in a moment. I'll tell you why it is this in a moment, but I want you to think, is the p-value going to be high or low? What does a low p-value mean? What does a low p-value mean? What does a low p-value mean? So know this concept. Low p-value always means statistically significant. When the slope is statistically significant, low p-value means unlikely by random chance. High p-value means likely by random chance. The p-value is the probability of our results or a result more extreme happening by random chance. So a low p-value means it is unlikely by random chance, i.e. statistically significant. And high p-value means, like, think about like probability of rain today. That's right there. So low p-value means that it's not that it's not due to random chance. It's unlikely. So if I told you there's a 1% chance of rain, you would say it's unlikely it's going to rain. If I say a 99% chance of rain, it's likely it's going to rain. So does it look like there's a relationship here, or this relationship looks to be likely by random chance? So answer this in the chat. This relationship looks like a relationship, or this relationship looks likely by random chance? Does this look like a random chance relationship or not a random chance relationship? It looks to be random, right? So if it looks to be random, the p-value should be what? High or low? If it looks likely random, like that looks just random, like not a real relationship, the p-value should be logically what? If it looks random, the p-value should be logically what? If it looks random, the p-value should logically be what? I'll take a guess in the chat. If it looks random, high, because it's likely that it's by random chance. And the p-value is this. I wasn't super close to it, but it was high. So be careful though. And this is an amazing example. The significance of the model is the significance of the what? And here's the p-value right here. The significance of the model is the significance of the what? And I'm going to draw some stuff to show you more about this. Yeah, we could, Martin. Yeah, Martin, let's do that next here. Remind me, Martin, right after this segment. Thank you, Jesse. And good work right there. The significance of a regression model is the statistical significance of the, starts with an S. The significance of a regression model is the blank statistically significant? And the answer is no, this is not. That's the same p-value used. So this model is not statistically significant because the what is not statistically significant. We said it was very flat. Remember what we said was flat? And we can do 10% after that, Sydney? Mm-hmm. So the what is not statistically significant here? What is not statistically significant here? The slope. Exactly, Hannah. The slope. Well, the p-value of the slope. The p-value of the slope is not statistically significant. So you say, but what about the intercept? Well, the intercept is not the XY relationship. So think about this. Which of these, model 1 or model 2, would imply to you a relationship between the two variables? Model 1 or model 2 looks like X and Y have a relationship. Model 1 or model 2. Which of those looks like X and Y have a relationship? Model 2. And think about this. What is the coefficient of the intercept for model 1? What is the coefficient of the intercept for model 2? The intercept is B0. So what is the coefficient of the intercept for model 1 and model 2? Model 1 has an intercept of what? About what, if you can read my handwriting over there? The intercept known as B0 is what for model 1? 200. And over here, it's 0. But the slope for model 1 is about what? What is the slope for model 1? The slope for model 1 over there is about what? The slope for model 1 is closer to what? Flat line, right? 0. Where this one looks to be about 1. So, because it's like, it basically right here hits that, like, if I could draw better, we're trying to make it so it goes through 100, 100. Try. There we go. So now it hits about 100, 100. So it's a 1, like for each 1 unit increase in X, we expect Y to increase by 1 unit too. That's the interpretation. So we have it increasing right there. So take a look. Going back to our example right here, you can see that the intercept is very high, but the slope is closer to 0. Now don't look at the value of the slope. Always look at the what of the slope to see if it's statistically significant. Always look at the what of the slope to see if it's statistically significant. Always look at the what of the slope to see if it's statistically significant. The p-value. Now here's the thing. You can technically look at the value of the slope in one instance. When could you look at the value of the slope and know for 100% certain that it's not statistically significant? When could you look at the value of the slope and know for certain it is not statistically significant? I think this will do it. When could you look at the value of the slope and know that it is not statistically significant? In what instance? Well, here we go right here. So when could you look at the value of the slope and know for 100% certain it's not statistically significant? And this is the instance right here. I know with certainty that this slope is not statistically significant. When the slope is 0. So do you know what the p-value will be now? So think about this, Ellie, you ready? And everyone else. This is the most likely thing by random chance. If there's no relationship, this is the most likely thing to see. So since it's the most likely thing to see, the p-value of the slope will be what? Since this is a slope of 0, which if there is no relationship, slope of 0 is the most likely thing to see, most likely the p-value will be what? How high? You're right, Hannah. It'll be 1. And there you go. So that's the theory, because 0 is the least significant slope. Be careful, because sometimes small units, like you would say, what if it's 0.2? Well, depends on the units we're dealing with. So you could have a very small slope that is statistically significant. It just depends on the units of your y variable. Like if I go here to analyze fit y by x. Oh no, we don't want to do this data. Just show one more example here, then we're gonna switch topics. We've been doing slightly complex stuff, which is good. Try to teach to all different levels. We want an x with a large span, like Facebook friends, and then we want a y with a low span. Okay. So if you were to think, oh, I can just look at the slope's value, look at this slope. That slope is 0.000000325. Now, it's not statistically significant, but you can't just look at the coefficient of the slope and be like, well, that's super close to zero, because it might be that your units of y have a very small span and your units of x have a very large span. You can actually see the slope over this graphic. So be careful. The only slope we know for certain that is not statistically significant is a slope of what? I'm repeating this for a reason. The only slope we know is not statistically significant for certain are slopes of what? A slope of 0. That is 100. We know that. We know the p-value. The p-value when the slope is 0 is going to be, we can just say here, analyze fit y by x. And for this data, we get a slope of 0 for the line. And if the slope is 0, which it says right there, the coefficient slope is 0, then the p-value has to be 1. What about the intercept? It's saying this means the intercept is not 0, but the intercept is not the xy relationship, so we really don't care.
It doesn't matter.
The intercept significance doesn't matter. It's all about the slope over here. The slope is the xy relationship. So really good examples right there. Please know your interpretations. Check out the Kahoot if you haven't. There's a lot of time. I'm just going to plug this video right here so we can do some new topics. So let me plug this in the chat. If you are looking for, and thank you for the 18 people watching right now, past live streams. Oh, there we go. Everyone's watching the Kahoot. Kahoot's getting a lot of views. Okay. Let me go to where I talked about the interpretations. Okay, here we go. So, and I did twice label an interpretation as slope. That is the slope interpretation right there. So interpretations can be found here. This is the Kahoot exam at 38 minutes in. Check out the interpretations. Just join that video right there. Open link into window, and you'll be here watching the interpretations right there. Good stuff. I think there was the true false. Let's write the, I'm going to put these in the notes. So we had someone say true false and 10% condition. So let's switch topic here at the 1 hour mark. And let's do Stat 201 review test. True false. And then we also have the 10% condition. Stat 201 10% condition. Who can link us for 100 points to the review material right now? Who can link us to the review material? Who can link us in the chat right now for 100 points to the review material? Where do we go for the review material? I'll do it here in a second. I just like for people to remember it. And then it's easy to do review 3. We'll do it in the future, though. We'll see. Thank you so much, Hannah, right there, worth 100 points. Right there, review 2 in the chat. And we're bringing it up right here. That'll bring you right to it. Thank you, Hannah. Mubot's a huge help right there. Let's go here to the practice exam. Let's go over these problems. There's no true false on here. Okay. Ooh, good stuff. I like it. So a lot of different chapters right here. Automatically see. Now, we need to know definitions. Definitions are going to be a huge help to us. What is extrapolation? I need a definition of extrapolation in the chat. So I need you to define what extrapolation is. Don't even worry. Like, as soon as you see it's talking about extrapolation, you need to think to yourself, what is extrapolation? Like, don't even read the rest of it. Be like, extrapolation. That's chapter 8. Well, you don't need to know what chapter it's from, called Regression Wisdom. So what's the deal with extrapolation? Don't read what they wrote. Think about what you think. Predicting, kind of. It can be used. So it's to elegant answer. It is used in time series. So extrapolating a model can be done in time series and is often done. That is true. Extrapolations are predictions that go outside the bounds of the X model. Ooh, I think we got that right there, right? So when you extrapolate a model, we like to say you're going outside the X bounds. So if we were to say we talked to 201 students and they studied between 2 to 10 hours for the test, and we're predicting their grades, and we see the grades something like this. Then we said, my friend did not study for the test. Why would it not be good to use this model? My friend did not study for the test. So here is the X bounds. My friend did not study, which these are hours, studied for the test. And this is grade over here. My friend did not study for the test. My friend did not study for the test. Have you ever had a class where you didn't study and you did really well? I've actually noticed that. I had a math class a long time ago. I think it was it wasn't differential equation, it was linear algebra. And I didn't really study for the test because I would come to class, I would do the work, and not every class is like that. I'm not saying like, oh, just come to class, do the work. I mean, I do think that's a huge help. But the way the teacher taught it was I would come to class, I would do the work, and then I'd be looking over my notes and I'd be like, well, I know this, I know this. And I just felt like I knew it all. So I didn't really study for the test and I did well. I didn't do well in every class. That was an outlier probably. So if someone didn't study for the test, they're not part of this model. So the data and 10 right there. Now think about your friend who studies 30 hours for the test. If someone told you I studied 30 hours for Stats 101, do you think they would make something like 140 or something? Do you think they'd be way over here? Do you think about how if someone says they studied 30 hours for this test, then what does that usually imply? What do you think about that? Like you're like, you say 30 hours for the test? That's a lot. 30 hours? Well, they're an outlier in how many hours they studied, and they're not part of the data that created the model. Like they're not between the bounds of the model. And we'd hope they have a higher grade, but sadly, and I do mean this, sometimes when you have to study a lot before the test, it's because there's a lot of knowledge gaps. So if you look, we want to look at maybe lurking variables like did the person go to class? Because going to class or not going to class, or did they do the assignments? Does that make sense? Now we're including lurking variables in our understanding here that this model should not be made to predict people outside the bounds for the X it was created on. So we created a model that predicts someone's grade from individuals who studied between 2 to 10 hours. So we wouldn't want to make predictions for someone who studied 0 hours, and we wouldn't want to make predictions for someone who studied for 30 hours, because both of these are extrapolations of the model that goes outside the X bounds. And there could be other variables that explain how well someone did on a test, like did you do the assignments? Did you come to class? Do you ask questions? Things like that right there are lurking variables. And a lurking variable is what? A variable that is what? How would you define this? Is just us reviewing more terms right here. A lurking variable is defined as what? A variable that is not your what or what. Here's more hints. So we'd say like study or something like this, or class, attend class, attendance. A lurking variable is something outside the XY relationship. So that right there is a lurking variable. It could be, it's a candidate lurking variable, we should say, because maybe attendance is what explains people's grades. And it, yeah, like attendance might explain how much you study. Attendance might explain your grade in the class. Now, your hours studied might also explain your grade, but there might be this extra third variable right here. I call it a Z variable a lot of times. Like you've got the XY relationship, but then there's other variables that are possible variables, and we can check it out by including them in model. We actually look a lot into this into 320. It's really easy to handle lurking variables. You just include them in the model. Like literally in jump, you would go right here and just go to analyze fit model. Wrong data set. Wrong data set. We don't have data there to work with. Analyze fit model. You just go right here and say, I want to explain someone's age, and I just want to do it with all these variables. And then you can see if they're lurking variables. There you go. So you can make a multiple regression. Fit model, add a bunch of variables, and then you can see which variables are actually explaining it. Major and honors program, interesting. So that's how you handle lurking variables. Good to see you, Carly. Lurking variables, not too hard to handle. You just put them in the model. That's not part of our test because we don't do multiple regression in this class, but multiple regression is just adding multiple x's. And what we do is technically called simple regression with 1x. So good topics right there. And extrapolation occurs when someone uses linear regression model to make a prediction outside the original scope of the independent x variable. Yes. Someone might say, well, is that the only time we extrapolate? Extrapolation, yeah, just making predictions. It can be used in other things too. Extrapolation occurs. But yeah, it occurs. That is not the direct definition, but that is extrapolation would occur. Extrapolation is predicting outside the bounds of your x's. And that is what you're doing right here. The independent, correct. I was like, they better not have thrown a trick, and I hate calling it the independent Just call it the x variable outside your x. Independent, dependent are just very mathy. Your explanatory variables. Event A is randomly selecting students from Brian's class making an A. Oh my gosh. Did Terry change these? Event A is randomly selecting a randomly selected student from Brian's class makes an A in Stat 201. Event B is a randomly selected student from Brian's class is a sophomore. Oh. Event A and B are mutually exclusive. Oh, this is so good. So, how do we check mutually exclusive? This is a review for you now to see how do we check mutually exclusive. We have a quick check we can do to see if things are mutually exclusive. We just need to check for ourselves right here, and then we can answer this very quickly. So if things are mutually exclusive and disjoint mean the same thing. So mutually exclusive. Actually, let's go to our notes. What is our quick check? This one's a super quick. We can get this right like that if we know how to check. How do we do it? See if you can answer. If I'm talking right now, see if you can answer it. And also write down these notes if you don't have it. We wrote down a lot of things earlier. How do we check to see if things are mutually exclusive? And that's the same thing as disjoint. Like these are the same terms. They're synonymous words. If one event happens, the other cannot happen. So does that make sense? And great job, Ella, right there. If one occurs, the other cannot occur. So what would that mean? If these are mutually exclusive, what would that mean? If they are, what would that mean? What would that mean? If these are mutually exclusive, careful, Michael. I wouldn't use those terms right now. So I wouldn't blend the terms. And thank you, Michael, for asking. I'll mention that here in a moment. But I wouldn't be very careful. Like when you talk about mutually exclusive and disjoint, don't bring in the words dependent, independent yet, because that is a higher level understanding to realize what they would be then. But when you do mutually exclusive, I want multiple to say it. Mutually exclusive literally means, and Ella's already said it right here. Mutually exclusive literally means, so only go to the terms only go to this right here and only worry about this right now. And Hannah's, I think, seeing it right there. If one happens, what? Andy, good to see you here. If one happens, what? And only go to what we have on the screen right here. If one happens, what? If one happens, what? And Carly's on the right track with the answer for the question. Good job, Carly. If one happens, the other cannot. Exactly. And this would actually mean they are dependent. But be careful. We've said earlier, and this is where people say, oh, so dependent is the same thing as all this. No. It's only that these are always dependent, but things that are dependent are not always disjoint. That's a higher level understanding, which go back and review the probability where we went over all the terms. But blending the terms is where usually people run into problems because they say, oh, dependent is the same thing as disjoint. No, it's just that disjoint events are dependent. That would mean, I like to use my classic example right here. If your parents say you're going to get an animal tonight, it'll be a cat or a dog, and they are disjoint. What are your parents telling you? If your parents say you can get a cat or a dog and it's disjoint, what are your parents telling you? What are your parents telling you? If it's disjoint, you can't get both. If you get a cat, you're not getting a dog. Now, you could technically not get either, but now use the lower term right here and tell me somebody getting a what would what on them getting a what. So think about how this now applies to it. So it is true that this then applies, that it is dependent because somebody getting a cat would depend on them getting a dog. And I guess I should mention why you might say, well, then aren't dependent events disjoint? We did an example earlier. The probability of snow is 1%. The probability of school off is 1%. What is the probability of school being off and snow on the same day? So there's a problem we did earlier right here. And when you see school being off and snow, you think I should what these events? school being off and snow, you think I should what these events? The probability of school being off and snow, I should what these events? Let me say, are these events disjoint? This is good right here. This is literally the same problem. Answer the poll in the chat. Are these events disjoint? I know this is multiplication rule, but I just want to know, are they disjoint? So yes or no. I wonder how we're going to do on this. What is our check for disjoint? Ooh, I'm very proud of the answers, I think, so far. So with disjoint, write a sentence for me that shows me if they're disjoint or not. We got about, remember, it's 50-50 if it's a guess. Ooh, we're going towards 50-50 now. How do we check disjoint? This is the same question we're just doing, and so you have to know how to do these things to check if things are disjoint. So how would you check disjoint right here? We are literally 50-50, which means people just guessed. We're right near 50-50. So write me your sentence to check if it's disjoint and then see if you can get it right. That's what it means, Jamarcus, right there. Yes, and Hannah has it right there. So Hannah, great job right there. So, and I want you to see the poll. We're basically a 50-50 guess, and these are people attending. So, and I want to say thank you again, 100 points again. Don't worry, this is the review. So what you have to say right here to check if they're disjoint, if this is true, if yes, then if it snowed, school can not be off. So that is not the case. School off, and this is snow. What do you know about school off and snowing? Good to see you, Caroline. What am I showing to you visually about school off and snowing right there? What am I showing to you about school off, having school off and snowing visually right there with the overlapping circles, which is the joint between them, which means they're not excluding each other, which is the idea of mutually exclusive. So what am I showing you? Well, kind of a little bit, Hannah, kind of a little bit. They are not disjoint, right? They can occur at the same time. Like sometimes we have school off. The blue region would be school off with no snow. The green region would be snow with no school off. But the overlap of the circles are times where they both occur at the same time. So be careful on the dependent word, though. This is showing you that they are what? Two words, blank, blank. I'm trying to show you here visually that they are what? Not what. Visually, I'm trying to show you they are what? Not disjoint. Exactly. There is a time where both can occur. Now we have to ask, are these two events independent? Okay, so let's do another poll in the chat here again. Don't worry if you get it wrong. Just want to see where people are at. So we have to know how to check if things are independent now. So this is a totally different question now. We have to know how to check if they're independent. What's our check if they're independent? How do we check to see if things are independent? So I need you to remember how to check independence. To check to see if things are independent, what do we do? So just write your sentence and be like, if they're independent, then what? What would it be the case? What would be the case of independence? What would be the case? You have to write the sentences because then you'll be like, what would be the case with independence? Ella has it right there. Perfect, Ella. Ella, every point button. Ella said, if they're independent, then the probability of school being off is not influenced by snow. So remember, independence, Isaac, right here means, and good questions, Isaac, independence means knowing one occurs would not change the probability of another. Knowing one occurs would not change the probability of another. So check out if you're wanting to review this, we did a whole section on this earlier. So if you just came in now, we went through and did a whole probability section right here going over these terms. Very important to know the terms because when you get here to are these two events independent, then knowing it snowed and we say if yes, then knowing it snowed would not influence the probability of school off. So what do you think right here? Is this the case? Knowing it snowed would not influence the probability of school being off. Is that the case, yes or no? Is that the case, yes or no? If they're independent, that is correct, Ella, right there. They are not independent. Because right here, if they're independent, then knowing it snowed would not influence the probability of school off. And if you look at our definition, or we could say changes the probability. We could use change right here. Would not change the probability. Knowing it snowed would not change the probability of school off. But that's not the case, because knowing it snows changes the probability of school being off. It is what, if it snows, school is more what to be off. If it snows, school is more what to be off. If it snows, school is more what to be off. More likely to be off. So school being off would what on snow? School being off would what on snow? Like having school off would what on snow? Would depend on snow, exactly. And so these terms are super duper important. Please write them down and look at them and then run these tests. Like if you want to ask if something is disjoint, say, okay, if A occurs, B cannot occur. So let's see. We did a big review right here. You ready? Is the answer to this question, the second question right there, true or false? I want you to read it over. Let's see how we do. So the question says, a student is a sophomore, a student makes an A. Are those mutually exclusive? So true or false? A student is a sophomore, a student makes an A. Are those mutually exclusive? Which one are you confused on, Martin? A lot of times people start to blend, like, wait, so disjoint is dependent. That you can reach that understanding, but don't start blending the terms. This is definitely false because, and write me a sentence, it is false that they are mutually exclusive. Why? So then when you have the understanding of why it's false, it is false because why? They are not mutually exclusive, and it is false because why? 100% false. It is false because why? And this is the answer to why. It is false because why? They are not mutually exclusive. So what is the sentence to explain the answer? This is the deeper understanding we're going for right here. So we've got definitions, we got answers. It is false because why? That is correct, Hannah, right there. And then you can say it's false because, and then you could say it's false because a student can be a sophomore and make an A. They can both occur at the same time. Does that make sense? Exclusive would mean if one occurs, the other can't occur. So right here, it's not mutually exclusive. A student could be a sophomore and a student could make an A. So it's not mutually exclusive. And don't use the dependent word right here because that's usually where people get confused is they start to blend the terms. Event A and B are independent. Knowing the outcome of event A changes the probability of B occurring. What do you think right here? This is a good review of what we just covered. So we did a really good review for all this. For two disjoint events, they can't happen at the same time. Yes. So independent means knowing, so independent only means knowing one would not influence the probability of another. So independent events cannot be disjoint. That is a fact. Independent events can happen at the same time, but it's impossible for independent events to be disjoint because disjoint events depend on each other. So that's a little upper level right there. But independent literally means, and this is what it means, knowing one would not influence. So this would not change. So this is the word we need right here. Not changes the probability, does not change. So this is false. We could have made this true also by changing this to what? Does everyone see this is now true? This is a true one now with the way I've changed it. If event A and event B are dependent, knowing the outcome of event A changes the probability of B occurring. And so that would mean they are dependent right there. Or you could put the not. You just have to flip it. Or you could say not independent. So another thing, someone could put like not, and then this would be a true statement if they're not independent. So this is false right here. If we wanted to change it to a true, we'd have to change it to dependent or not independent. Two events that are independent have equal probabilities of occurring. Okay. So I want you to think about this. We did an example earlier. We might still have it up. Why are your favorite basketball and baseball teams winning independent of each other? Why are your favorite basketball, and we had it here earlier, your favorite basketball and baseball teams winning independent of each other? Your favorite basketball team has a 60% probability. Explain to me why your favorite basketball team and your favorite baseball team are independent of each other. Totally different problem here. But explain to me why these are independent. We have your favorite baseball team and your favorite basketball team. I think Hannah might be saying it right there. Give me the context of it. Like, fully, you're doing a great job. 100 points right there. So we got a problem right here. Favorite basketball team. Baseball team has a 70% chance of winning. Favorite baseball team. Basketball team has a 60% chance of winning. Your baseball team winning would not influence your basketball team to win. Does that make sense? You might come up with some weird scenario, like maybe there's someone like Michael Jordan playing on both teams when he did baseball, basketball. Maybe he's tired because he just played an earlier game. We won't try to go that far with it. We think that these are mostly independent. Boom, right there, Carly. That's exactly what independent means. Because if the baseball team wins, that does not influence the probability of the basketball team winning and vice versa. Both probabilities are independent of each other. And what do you notice about these probabilities? These probabilities are different. So what does that tell you? Two events that are independent must have equal probabilities of occurring. So this is very clearly what right here? Two events that are independent must have equal probabilities. Clearly false. Just means that they don't influence each other. So clearly false via that example. If you want to see it again, just an example we made up with two independent probabilities. And you can see right here, they are not equal. We could have made them equal. They could be technically equal. So you could write they could be equal. It's possible. They don't have to be, though. And then the must-have right there. The sample size needed to estimate a population parameter. Oh my gosh. What in the world is this one? The sample size needed to estimate a population parameter is not these nots. Oof, I do not like this question. Is not determined by taking some fraction of the population. Yeah. True right here. So that's n. I'm gonna double check with here. The sample size n need to estimate a population parameter like mu or p is not determined by taking some fraction of the population. That is a true statement. I'm going to double check with the key right here. It's just a very oddly worded question. I do not like this last true false. Just with the knots and stuff right here, a little bit confusing. We really, and this leads into something we'll do here in a moment. Someone asked, thank you so much. When do we worry about the relationship between these two? When do we worry about the relationship between those two right there? When do we worry about the relationship between these two right here? There's a very important time where we worry about the sample size and the population size. A very important condition someone asked us to review, which we're reviewing next right here. Very important thing right here. When do we worry about this? We worry about it not with random, not with success failure, not with large enough n. We worry about the relationship of the sample size to the size of the population or the fraction of the population we have when we worry about the what condition. And it would be that n is less than 10% of the population. And it's the 10% condition right there. The 10% condition. So I'm 99% certain. If I got that one wrong, I'm going to be shocked. Let's go see. And last question is a little. What? It says false. I'm going to talk to Terry about this. The sample size needed to estimate a population parameter is determined by taking some fraction of the population. I think this is true. Is not determined. I'm going to talk to Terry about this, and that I think shouldn't even really be on this. This concept relates to things we will get to. There is no margin of error on this test. Very sorry about that. It should be removed from here, but there is no margin of error. I think there's one margin of error question right here. It shouldn't be on here. 6895 does apply, and so there is no margin of error right there. I think it's because this question has sampling distribution stuff on it. So we do have sampling distribution right here with the large enough n. We draw the sampling distribution, and then someone makes a confidence interval at the end. So it's basically a question that has like one part. How is the sample size determined if not taken? Let me look at it again. The sample size needed to estimate a population parameter is not, so they're saying it is determined. The sample size needed to estimate a population parameter is determined by taking some fraction of the population. I just do not like the way this is worded. Are they just saying like, no, it's saying like the sample size we need, n, to estimate some mu or p or some other thing is determined by taking, I mean, that's what we do when we take a sample, is we take some fraction of the population. Unless they're just being redundant. I swear this question, I've never seen it before. Because, but it's saying to determine the size of n, pretty sure this is not true. Fraction. Saying take n, take like a certain thing of it. I do not think there's any questions like this on the test. I've looked over the full test. How's the sample size determined if it's not taken? Well, that's what the sample size is, but it's saying like the sample size we need to estimate. So it's saying needed to estimate, which is kind of the key in here. Is saying the required n needed to estimate, like as though we need some minimum sample size n. So it's not really the size of the sample we take; it's how we take it. So Ella, I actually think this is true right here. I think the problem is, so this is true. It's how we take it. It's not how much we take of the population. All the formulas we use, especially later in the class, what do you notice is important in this formula down here? What is important in this formula? The important thing in this formula, I would not memorize this. I do not agree with this question. I'm going to ask Terry about it because I think this is a question someone incorrectly marked. We have made errors on a key before. I think this is one of these instances. So very sorry about that. This right here has n, and it doesn't have any capital N, which is population size. So we are not using the population and thinking about some fraction of the population to estimate mu, which is what this interval estimates, with an estimate of the sample mean. It's all about the sample size. Does that make sense, Hannah? The sample size is what we use, but we do not figure out a needed sample size via capital N. Frankly, the only thing related to this would be the 10% condition. So there's no capital N in this formula. Capital N does not exist. We're only using sample size to estimate the true mean from the sample mean to create a confidence interval. And I think this is a confidence interval question. I'm literally going to email this to Terry. Let me go back to the main screen. 10% condition. Say, I'm pretty sure this is true. Okay, let me go here and email Terry and be like, I think this is true, because we need to update this on the first time seeing that. Right here. An email called "This is dangerous," but I think it's one of those spammy emails from like all right, send an email right here. I'll show you the email real quick. This is dangerous. Yeah, it's a spam email. Just insert whatever party and then just say the other party's dangerous. Just be like, this party's saying the other party's dangerous. Oh my gosh. Yeah. Every political email ever. This is dangerous. This party says this. All those emails. Show you my email real quick. Sorry. Okay, here we go. And then let's talk to 10% condition. I just noticed now it's sent out there will be interpretation questions. How many interpretation questions are there? How many interpretation questions are there? Then we talk 10%. There's the email I sent. I think this is a margin of error question, but fraction of the population we sampled shouldn't matter. It's how we sampled the population that matters. We only use n in formulas and not capital N, so we don't even consider the size of the population outside the 10% condition. It'll be written interpretations, and how many written interpretation questions will there be? How many written interpretation questions will there be on the test? Very important right here. How many written there'll be 3. What 3 things will you need to write full interpretations for? What 3 things will you need to write full interpretations for? Full interpretations, like full sentences. What 3 things will you need to write full sentences for? Let's do conditions. What 3 things do you need to write full sentences for? Slope, intercept, R squared. Full sentences. If you say the intercept is this, the R squared is this, you get like half a point. No. Stat 201. Conditions for sampling. Or let's just do conditions. Conditions for test 2. Okay. Let's do all the conditions right here. I think that's where we'll end off, but let's do it. Here's all the conditions. What was the very first chapter we did, which we're actually mentioning in the chat right now? And what is the very first chapter we did that had conditions requiring us to meet certain things? I guess there's other conditions like things are independent, they're disjoint, regression, right? So we have regression right here. And regression has how many conditions? And if you in my class, you probably know it pretty quickly. Blank, 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 blank. So what are the 4 conditions for regression? Which it's basically the 3 from correlation with an additional 1 right here. So the 4 conditions for regression are QQ, straighten up, no outliers, plot doesn't thicken. So QQ means 2 quantitative variables. You can call it the quantitative variables condition. 2 quantitative variables. Literally just means you're doing like height and weight or anything that's quantitative. And if you don't do height and weight, you won't get a regression. So we could go over here to data like this, and we can analyze fit Y by X, gender with born in Tennessee, and we get a mosaic plot right here because it wasn't 2 quantitative variables. Only 2 quantitative variables shown to you on the left will lead to a scatter plot, which is the visualization of 2 quantitative variables, which will lead to regression. Other combinations will not lead to regression, so you have to have 2 quantitative variables. I like to call it QQ for quantitative X, quantitative Y. Straight enough. Now, this means the line goes through the center of the data. So when you think about straight enough, we don't call it the perfectly straight line condition. We say straight enough because that's probably good enough. This would be a slight problem area right there because the points should be, go to the Stat 201 review page. And there's the review videos on there, Kendall. Yep. And so here, that's probably good enough. But this is where it's not straight enough. This is where it's not straight enough. So that's got a strong bend throughout the model, not straight enough. The line goes through the center of the data, and right here it's not. I mean, it might be going through right there, the middle of the data, but it's not going through the center of the data. No outliers is probably the easiest one. Because what does no outliers literally mean? So no outliers is probably the easiest one. Because it literally means there are no, and we say strong outliers. We try to make it obvious on the test if there's outliers. So when you think about no outliers, don't worry if there's something like that, right? That's iffy. Like, that's iffy. We don't like to give iffy ones like that right there. Preferably on the test, a lot of times, we like to give you something more obvious. We do have ways in upper level statistics to check for these things to see if something like this is an outlier, and that would be a problem with the no outliers condition. Did Mubot not put review 2 in the chat? Is chat not connected? Can people see my chats right now? Mubot should have put review 2 in the chat. We're still connected, right? Oh, there he goes. He's putting review 2 in the chat right now. There we go. What happened? Why did Mubot not talk to us? Mubot, give him 100 points. And now plot doesn't thicken is a very important condition that I think a lot of people don't fully understand. So we're going to talk about it for a little bit right here. So plot doesn't thicken. There's some, and we could say right here, the strength of the model is constant throughout i.e., as in there is the same thickness. So when you think about strength and correlation, which we can kind of see in regression also, is how tight the points are around the model. So this has constant strength. So the predicted power of a model should what? Increase, decrease, or stay the same throughout the model. The predicted power of a model should what? Should it increase, decrease, or stay the same throughout the model? The predictive power of a model, should it increase, decrease, should stay the same exactly. The predicted power of this model, and there's a lot of, there's a few My Pearson questions that do this. This model is getting water as it goes across. As you go across X, the predicted power of this model is getting water. As you go across X, it's getting water. The predicted power of that model is getting water. So it's how well does the line make predictions, and it's getting water. It is heteroscedastic, yep. It's getting weaker. So would it be better if it just got stronger? What if the predicted power of the model got stronger as we go across the x-axis? Is that good? So we take a model like this, and we spread out the points here to start, and the model gets stronger by the end. So is this good right here, that the predicted power is getting stronger? Is that good right there? What do you notice? Nope, not good. And so it's getting stronger right here, but this is a problem because the plot is whatening. Now, I know it's not doing it in the positive direction, but the plot is whatening. So this is the only good one right here. This is bad. It's different thicknesses, right? So we don't want thickening at different points in the plot. We want constant strength, which is what homoscedastic is. These are big words for that. So how can we check this? Like, what could we make with this to check this? So oftentimes people use this to check this right here. And we could just turn it into one of those by saying, okay, let's take this and let's go here and do this. And that's how we do it. So we don't have any fun ones. Our graphics are kind of boring. Oh, then go here. Go here. No, we're going to go to this one. Go here. And go to plot residuals. There we go. And there's the residual plot right there. So that just takes the line and makes it flat. You can see this point way below right there. That's the point below over here. So you just take the line, make it flat. There's many ways to do it, but my favorite way is just to make the line flat. And you can see the residuals. So best checked with a residual plot. So definitely check that with a residual plot to make sure you got it right there. Good stuff. And those are the conditions. QQ straight enough. No outliers. Plot doesn't thicken. Used for regression to see if we are properly doing a linear regression of X and Y. Good to see your Axu. And so now we get into the following. We would talk about sampling distribution of the sample proportion. How do you know you're doing proportion versus category versus means? How do you know you're doing proportions versus means? How do you know you're doing the sampling distribution of the sample proportion? How would you know that? It's categorical data, cat or quant. And that's exactly right there, that categorical data is when we're dealing with proportions. And now for the remainder of the semester, this is how we do it. You ready? We will do conditions for multiple chapters. And how many conditions will we just do like this? Don't do it for the first one. This is not where you go and say your conditions just like, but how many conditions do we just rattle off for the remainder of this semester? So this is a little memorization. Not the best to memorize everything, but this is for the remainder of the semester, we're just going to knock out how many conditions really quickly and easily. How many conditions will we just be like, boom, boom, for remainder of semester from here on out? Every chapter going forward. Not 3, though. There are 3 conditions. But we can't just do all 3 instantaneously. The only conditions we will say really quickly are what? How many? Not 3. There are 3 conditions, though. How many conditions can we just be like, condition 1, condition 2? Sydney has it right there, random and 10%. So random means our data is selected randomly. Sometimes on My Pearson, they will break this into random / independent. If things are independently selected, they are random. So sometimes they add in a little extra independent, but independent would mean one does not influence the other. So something that is independent of another thing would be random of it. I mean, everything is important. So we're going over the conditions right here. Random, we just make it very easy, especially on our tests. Just was it randomly selected? The trickiest way we ever did this was someone waited outside of Walmart and talked to people, and then we didn't say it was random, and people put, oh yeah, random. I assume they randomly talked to people. We will usually just tell you it's randomly selected. You'll see it in the problem. We'll say like a random selection of this, a random selection of that. So don't just assume it. On our test problems, we tell you if it is random. So if we say it's random, it's random. We just usually make that easy to be like, we did randomly select this. So that's usually one of the easiest ones. And sometimes on my Pearson, they break it apart into two conditions. But if it's independent, then it must be random because independent things would not influence the other things. So that's how they sometimes deal with it in later problems. 10% means what? What does 10% mean? So this is the second condition for the remainder of the semester when we do sampling distributions, confidence intervals, and hypothesis tests. So you're learning test 3 material right now too. What does the 10% condition mean very specifically? And then how will we check it? What does the 10% condition mean? What does it mean? Sampled less than 10% of the population. Sample size. So there's two things you need to identify for every problem that asks you something like this. What are the two things you must identify to solve a problem other than knowing the terminology right here? What are the two things you must identify? Knowing the notation is the key to doing this. There's two things you need to identify here, and we'll write out the math for this. So what do we need to identify? So we need to identify sample size, which is n, and then we need is less than 10% of, and then we can put right here, population size. So this is how, it capitalized that n right there, lowercase n. The sample size is less than 10% of the population size. So don't just guess at these questions. Don't just guess at them. When you see a question and it says something like, we took a sample of 500 and 60 of them came back with defects. Make around 1 million a day, or yeah, sure, whatever. Do we pass the 10%? Okay, be very careful right here. Do we pass the 10% condition? Let's start a poll. Do we pass the 10% condition? Well, so tell me the values. Tell me the values. Identify the values. That's the key. So remember, think about what you have and write down what you have right here. Put the notation in the chat if you want. Put the notation in the chat for what you have. So what's the notation? See if you can tell me the notation. I did try to be a little tricky with this. So what's the notation? Ella, 100 points. Yep. What's the remaining notation, Ella? Ella, for another 100 points, what's the remaining notation? You are correct, Ella, right there. Perfect answer. And so I think Ella answered it correctly. So when you get one of these problems right here, do we pass the 10% condition? You need to be able to say, this is the sample size. This is the population size. Because we make around 1 million products a day. We took a sample of 500. So what is 60? That was the tricky problem to this. So what is 60? Does anyone know what 60 is? Another 100 points. What is 60? It's X. Now talk to me about this. Blank percent of our blank was defective. We do meet it though. This is yes. Yes. So this is a calculation of what right here? Oh, no, don't worry. This is the practice. This is why I throw tricky questions on here. This calculates what right here? What did this calculate? P hat. So what does this mean? Blank percent of our blank was what? Which is not, that doesn't matter with the 10%. That's why I tried to trick everyone here, or, you know, made it a little tricky. What does that mean? Like, tell me what that means right there. Blank percent of our blank was blank. What does that 12% mean? What does it mean? Like conceptually. 12% of the sample was defective. Exactly, L. Exactly. So 12% of the products we sampled, and make sure with the sample right there, it's the sample proportion. 12% of our sample was defective. So you can check the 10% condition a lot of other ways, though. That's not the 10% condition. That's just the sample proportion. We would say you could do 500 out of a million, and you could see we actually whatted. If you had to write a sentence, you could say we sampled what, like 0.5%? So 500 divided by... And so we sampled 0.0005% of the population that day. So we definitely sampled way less than 10%. So you could also times this by 100 to look at it as a percent. We sampled 0.05%. Does that make sense right there? Yep. And great job, Caroline. So we sampled way less than. So you can look at n divided by capital N. And this needs to be, so this is n divided by capital N. And this needs to be less than 0.10. So that's the way to check it right there. Was your sample size less than 10% of the population sampled? So really good check right there. Understanding what the condition means. Is my sample less than 10% of the population size? Really boils down to knowing the notation. So I do like to throw problems with extra notation here so you know what to look for. Like, this is the amount of successes in the sample. This is the sample size, and this is the amount we're sampling from. We make 1 million products a day. We took a sample of 500, so that's the population we're taking from all the products made that day. Now make sure, we say this in our class all the time, before you get to the next condition, what? Oh, we did some at the start, Claire, sorry about that. We did this some at the start. Check out the start of this video, because I'll be teaching here soon. But at the start of the video, we did a lot of probability problems. We did a good 42 minutes right there of probability review at the start. So check it out. What do we do before we do the next condition? Before we do the third condition, we always what? Before we do the third condition, we always what? We always pause. Put those pause in the chat right there. We always pause. Now, the reason we pause is because a lot of times people are likely to say, and they'll say this often, they'll say success, failure. But here's the thing. That's the right condition right here for proportions. This is what determines the third condition, is what kind of thing are we doing right now? We're dealing with categorical data. Since this is categorical, like, is a product defective is categorical. And we could say right here, the company claims a defect rate of 10%, or that's the same number, of 5%, sure. Is this odd? So there's a full problem right here. Company, well, let's just do this. Let's make it, sure. The company claims a defect rate of 5%. Do we pass the success/failure condition? Okay. So the company claims a defect rate of 5%. So this is the claimed what now? We have N, we have X, and this is the claimed what? Great job right there, Sloan. Then 100 points right there. This is the claimed what in notation. Notation is very important. We'll see it when we go back to the notes right there in a moment. This is the claimed what. They claim a defect rate of 5%. So this is the claimed what? It's the claimed defect rate. They're saying it is the what? Not p hat though. So p hat will be what we saw in our sample. So we saw in a sample a defect rate of, so this is p hat over here. We saw a defect rate of 12%. This, in Caroline, great job right there. Good practice. This is what they're claiming is the truth. So they're saying the true defect rate is 5% and the true not defect rate is 95%. So that's the claimed truth. And you'll notice this is going to be very important because we must have at least, and we'll never put it to exactly 10 successes and 10 failures from a possible sample. And we'll just say this. I don't want people to be confused. That is what it is, though. This is checked with NP greater than or equal to 10 and NQ greater than or equal to 10. So, yep, and great job right there, Sydney. Good practice. No worries. This is the good practice right here. So we just check it by plugging in the numbers NP greater than or equal to 10 and NQ greater than or equal to 10. What relationship do these share when you solve for the values right there, which are going to be 0.05 times 500 equals 25, and then 0.95 times 500 equals 475. Not equal to 1. Good. Now technically P and Q, adding these up, add up to 1. But NP and Q add up to what? NP and NQ, if you add those up, those add up to what? So NP and Q add up to not 1, though. So when you add up NP and NQ, they add up to what right there? The sample size of 500, exactly. So the proportion and the complement of it do add up to 1, but now you're saying this is the amount of expected successes, this is the amount of expected failures, so we expect 25 successes, we expect 475 failures. A success just means whatever we're interested in. We're interested in defects, so it's weird to say a defect is a success, but success literally just means the thing we're interested in measuring. So whatever you want to measure, you want to see at least 10 of what you're measuring, and you want to see at least 10 of what you don't want to measure. Now, why is it important we pass the conditions? Why is it important we pass the conditions? Like, let's say, for example, we sampled from 200 with a defect rate of 1%. Now we'd only expect 2 defective. Why is it important we pass the condition? Thank you, Caroline, right there. Good questions. And Caroline, 100 points. Great job today. And everyone else, great job. Why is it important we pass the conditions? Exactly. By passing all the conditions, the curve will be normal. Notice how there's only 2 expected successes here with this rate. What is the expected failures with this rate? So think about the math you could quickly do. Since we know the sample size, that is correct right there, Aksu. Success failure is for categorical only. What is the amount of expected failures? Well, the failure rate right here, if that's the success rate, is this. And the amount we sample is 200. So the expected failures is what? If there's 2 expected successes, then how many expected failures would there be? Which I'm solving the math over to the side. So if there's 2, or the failure rate is this, how many expected failures would there be out of 200? Why does it keep making that look different? Oh, maybe I'm not typing it. 198. Because 198 plus 2 equals 200. So you could also see it would fail if we did it this way. It would just be the other skew. But as we get more expected successes, and there's where we get 10 expected successes, the curve becomes way more what? You can see with very few expected successes, it's skewed. But the whole point of meeting these conditions is with enough expected successes, at least 10 expected successes and failures, it becomes more normal. And it'll become perfectly symmetric at a 50-50, but it's normal enough. Don't think normal enough. This is a success failure condition. But it becomes normal enough for us to, I keep saying that, but do realize these are the conditions. We do have a condition called nearly normal coming up later in the semester. So I don't want to confuse people. And sometimes we put that as a trick question on this test. But here's what I'm going to do is I'm going to take all this right here and quickly copy it, because now we're going to do conditions for the sampling distributions of the sample mean. And by doing the mean, we'd have to ask someone something like GPA or height or weight, because those are all what questions, or the weight of a bag of M&Ms, or the weight of people on a balcony, because those are all what questions. If we're doing the distribution of the sample mean, where we incorporate the normal entire, right here. Those are all quantitative. So, and we'll talk about that. We'll show that here on the last condition. So all these conditions right here are identical. That's why I'm not really going to go over them. We do have to pause right here, and we have to think about what we have up here that we're doing the distribution of the sample mean. And the third condition right here is going to now be what? What will the third condition be now that we're doing the sampling distribution of the sample mean. The third condition will be what large enough n. And this is where the central limit theorem, and it's technically lowercase n, still 100 points though, technically lowercase n because large enough sample size. So it might have it in the notes capitalized. That the small things are sometimes so important. And thanks to Emil Williamson, one of the awesome people out there who one time during a Stats 1 review, I was putting in wrong notation. And he's like, Brian, that should be a mu instead of a y bar. So he taught me the particular nature to being exact with what we write. So large enough sample size is what we need. And so this says, well, we've got the conditions. Here's the steps. Well, let me write what it means. The sample size is large enough that the distribution of the sample mean is normal. Okay. This is key. The sample data, what a guy. The sample data will have what shape as n increases? Be very careful. The sample data will have what distribution as sample size increases? So here is a very skewed distribution. For larger n's, the sample data will have what shape? This is a trick question. The sample data, you are correct, because the sample data is going to look like the original data. The sample data looks like the original data. What becomes more normal and tighter? So this is what Sloan was talking about. The what becomes more normal and tighter? There's the answer right here as we do it. What becomes more normal and tighter? So every blue dot down here, maybe I'll show it again. This is one of your things. Every blue dot is the average of 25 dots. So the sample data will look a lot like the original data. Email the SI leaders. Good question for them right there. Thank you for asking, Matthew. I do not know the answer to that. So the what becomes more normal and tighter, and this is very key. The what becomes more normal and tighter, not the sample data, not the original data. Here's the original data. It's very right skewed. The sample data will look like the original data. What becomes more normal and tighter? The distribution of the means becomes more normal and tighter. The distribution of the means of sample size 25. As the sample size increases, the sample data looks like the original data. So if you went out and talked to students, you would see very skewed data if the data is skewed. That's what your sample would look like. But the means possible via the sample data are going to be more normal and tighter as n increases. Here's a small n, here's a larger n, and here's probably a large enough n. So what is the first thing we do when checking the large enough n condition? The first thing we do is we look at the what of the data. Step 1 to check the large enough n condition is to look at the what of the data. What is the first step? Boom, look at the shape of the data. So where'd our conditions go? Oh, don't tell me I lost that word sheet. No. This is what happens when you have a million Word documents open. Here we go. What Word document? Document 33. Okay. Step 1. Look at the shape of the data. So it's either going to be normal, skewed, or very skewed. Step 2. What is the required size? And it could be very, very, very skewed, maybe like 500. Exactly what is the required size? And notice, the more what it is, the more what we need. Think about the condition name. So the more what it is, the more what we need. 12500, boom. The more what it is, the what or what needs to be. So the more skewed it is, the larger n needs to be. Step 3, do we have, oh my gosh, at least this sample size? What's the required sample size? Okay. Exactly. Do we have at least, is our sample size n large enough? Exactly. Which then, Sloan, I like that even better. Is our sample size n large enough. At least this size. Let's say large enough. Yeah. At least this. Yeah, which is the large enough n. So one of my classic questions right here, and let's do it. So yes or no in the chat. I'm going to do a sample size of 2 from this. So is a sample size of 2 large enough to meet the large enough n condition right here? Is a sample size of 2 large enough to meet the conditions, randomly select them, less than 10% of the population, and do we have a large enough n that this distribution will be normal down below? So what's the first step? So just follow through with the steps with me right here. First step is what? For those who don't know the steps, first step, we just said it a moment ago. Check out the piece of paper we wrote it down on. The first step is what? We're taking sample sizes of 2, and every blue dot is the average of 2 dots. So the first step is what? Look at what? The shape. So what's the shape of that? What is the shape of that right there? The shape of it is what? What is the shape of it? So the first step is look at the shape, and the shape of that is what? So what is the shape of this? It's normal. So what is the required sample size, which this is our sample we're taking. What is the required sample size for us to, what required sample size? 1, right? Are we taking a sample size of at least 1? Are we taking a sample size of at least 1? And that answers the question of, do we meet it? That's step 3. Do we have that required sample size? Are we taking at least, because it's 2? And it would have been fine if it was 1. The distribution is normal. Just think about this. This lower distribution, 2 things right here, Sloan, this is what you were saying. The 2 things we should know is that the lower distribution is just what, and what. What 2 things would you say about the lower one? It's just going to be more what and more what, which you can see it right there visually. More normal and tighter, which is what the central limit theorem says. So think about this. If it was already normal up there, it's more normal here. So since it's normal up there, it'll be normal down here. So as The Rock would say, it doesn't matter. It was already normal to begin with. It'll just be more normal, so it's already normal. So really good stuff right there. And we went a little bit over today because really good review. And so if you want, check this out. I mean, this was a power review right here. Please come to class on tomorrow. That's what we say, on tomorrow. Because we'll be doing new chapters tomorrow, and hearing it definitely is going to help you out. You're welcome. Great review. I think we did everything, actually. Man. Well, that's got it. Bye for now, everyone. Bye.